Hey there, fellow space enthusiasts! Today, we're diving into a fascinating discovery that's shaking up our understanding of the Sun. You see, the world's biggest solar telescope has caught something incredible: vortexes on the Sun's surface. But this isn't just any old solar phenomenon, it's a game changer. So, buckle up as we explore why this discovery is so significant and what it means for our understanding of our star. First things first, let's talk about the Kelvin-Helmholtz instability. This concept, first worked out in the late 1860s, explains why wind causes ripples on water and why clouds shear into rows of curves. It's all about fluids sliding past each other at different speeds, causing the boundary between them to buckle, curl, and roll up into vortexes. We've known about this instability for a while, but we've never been able to confirm that it happens on the Sun's surface. Now, fast forward to April 14, 2025. The Daniel K. Inouye Solar Telescope, the largest solar telescope in the world, entered its operational phase. During a 3-minute window, a team led by David Karidza and Friedrich Wogger pointed the telescope at an active region near the center of the solar disk. What they saw was something extraordinary: vortexes, or solar swirlies, on the Sun's surface. But why were these vortexes so hard to spot before? Well, it's all about scale. The vortexes are incredibly small, and the diffraction limit of telescopes with mirrors smaller than 2 meters meant that we couldn't see them. The Inouye telescope, with its 4-meter mirror, changed the game. By pushing the wavelength to 416 nanometers, the team achieved a higher diffraction limit and higher resolution, allowing them to see these tiny vortexes for the first time. What did they find? Well, the interfaces between concentrated bundles of intense magnetic fields and the surrounding granulation were dominated by vortex-like structures and fine dark striations. These vortexes were usually between 60 and 100 kilometers apart, with individual vortexes measuring from 25 to 170 kilometers in diameter. The smallest ones they could spot were right at the 19-kilometer resolution limit, which means we don't know how far down in size they go. Now, here's where things get really interesting. The vortexes were growing and propagating along the interfaces at speeds between 0.67 and 3 kilometers per second. This means that if you were hovering above one of these boundaries, you'd see something like rolling cloud-like things, but then, suddenly, everything turns into chaos. It's like the peaceful phase is over, and you're left with very chaotic turbulence. So, why do these curls form at the interfaces and not elsewhere? Well, it's all about the direction the magnetic field is pointing. Magnetic field lines act like elastic threads running through the plasma, and they resist being bent. When those threads lie along the direction of the flow, they pull a rippling boundary back, which flattens and suppresses the instability before it can grow. But when they run across the flow, they do nothing to stop it. In the strong magnetic regions observed by the decayist, the field points almost straight up out of the surface, while the granular flows sliding past it move sideways. The threads are strung the wrong way to hold the boundary together, so the curls grow with nothing to limit them. This is a stirring mechanism where none was expected to exist, and it means that magnetized and unmagnetized gas can blend into each other. Now, here's the real kicker: this discovery has implications for our understanding of the Sun's corona, the million-degree outer atmosphere. We've never observed the mechanism responsible for shuffling field lines at their anchor points, but this new understanding suggests that twisting motions at the surface of magnetic elements are braiding of the magnetic fields. This could help us understand how the corona is heated and how energy is released in eruptions and flares. But wait, there's more. We still don't know how small these Kelvin-Helmholtz patterns get on the Sun, and we're not sure how things work in computational simulations when we need to reach those resolutions. We need to do more investigation and extend the observations beyond the current 3-minute window. This is the next challenge and the next milestone. In my opinion, this discovery is a game-changer for solar physics. It's like finding a hidden mechanism that's been right in front of us all along. It raises a deeper question: what else are we missing? What else is out there waiting to be discovered? So, what do you think? What makes this discovery so fascinating to you? Let me know in the comments below.